In this video, we're going to look at the solution to the problem of message passing agreement in multicores. This solution is presented in more detail in the paper Consensus Inside by myself, Rachid, Guerraoui and Maysam, Yabandeh, which appears in the Middleware Conference of 2014. So let us first look at why this problem is interesting. Future hardware is expected to be more diverse and even more complex than what we have today. This trend will introduce problems to software systems. In the classical shared memory view of multicores, the portability from the point of view of performance and scalability of concurrent systems will be problematic. A solution that has been proposed to this problem is to replace the cache-coherent shared memory approach with explicit message passing. In this view, local copies of shared data will have to be kept consistent using an explicit agreement protocol instead of the classical cache coherence protocol. In the context of multicores, the only approach that has been tried in order to solve this problem is a protocol called two-phase commit. The problem with this solution, however, is that it's blocking. Two-phase commit is a blocking protocol. So is this problematic in the case of multicores? Well, yes it is. You might have scheduling decisions or I/O events which might significantly delay some processes. And in a blocking protocol, the overall system is only as fast as the slowest participant. So the alternative to such blocking protocols is to use non-blocking protocols. Non-blocking agreement protocols are usually referred to as consensus protocols. The best known such protocol is Paxos. So Paxos only needs responses from a majority of nodes in order to be able to make progress. So Paxos comes with a lot of variations, but our results show that all of them have a problem in the multicore environment. They use too many messages, which makes them not scale. To understand how Paxos works in the common case, we're going to look at its most popular version, multi-Paxos. So each physical node of Paxos has three agents, each fulfilling different roles. There is a proposer, whose essential role is to advocate client commands. There are acceptors, whose role is to resolve any contention between proposers, and learners, who represent the actual long-term memory of the system. So they actually represent the replicated state. And as I said, these three roles are usually all deployed on one physical node. And these nodes containing all these three agents are replicated in order to be able to run the Paxos algorithm. In order to apply an update, proposers broadcast the update to the acceptors, which, if the message is what they expected, broadcast it to the learners. Upon receiving messages from a majority of acceptors, the learners actually apply the update. The problem, as I just said, is these are too many messages. They cause scalability issues. So what can we do? Well, our idea was to only use one acceptor. So while we still have the acceptors on all the replicas, we only use one as an active acceptor and keep the others as backups. What this means from the point of view of sending messages in this protocol is that the proposer will only need to send one message to the active acceptor, and only this acceptor will have to broadcast to the learners. If we make abstraction of the messages being sent between agents on the same node, so between an acceptor and a learner on the same node, we've just gone from sending 8 messages in a system with 3 replicas to just 3 messages sent between physical nodes. That's a significant reduction. We call this resulting protocol one Paxos. Of course, there is a small trade-off. With one Paxos, as long as the active proposer, the so-called leader, and the active acceptor are not responsive, the system itself is not responsive as well. But we think this is a reasonable trade-off to make. However, if other random nodes fail, we offer the same guarantees as the default version of Paxos. In our paper, we also try to evaluate and see how one Paxos does when compared to two-phase commit or multi-Paxos in practice. What we observe is that one Paxos offers increased throughput, decreased latency, and overall increased scalability. In addition, we also notice that one Paxos has an extremely small recovery time in case of node failure. In this video, we've only provided a very brief summary of our paper. For a more detailed study of the particularities of the multicore environment, for a more detailed explanation of how the one Paxos protocol works, and for more detailed evaluation, you're invited to consult our paper.